Hi, my name is Krudant and I'm going to present the slides on image sensors. This is the general flow of the PPT in which we'll first understand what image sensors actually are. Then we'll go on to the two types of image sensors, CCD and CMOS. CCD standing for charge coupled devices, whereas CMOS is complementary metal oxide semiconductors. Then we'll see the advantages and disadvantages of CMOS and CCD sensors. Then we'll go on to the applications and conclusions for the same. Let's start with the very basic. What is an image sensor? An image sensor is a device that captures and converts light into electronic signal. There are two main types of image sensors: charge coupled devices CCDs and complementary metal oxide semiconductors CMOS sensors. CCDs are known for their high image quality and low noise, while CMOS sensors are more energy efficient and can read out data faster. So how does an image sensor work? At high level, image sensor consists of a grid of light sensitive pixels that converts light into electrical signals. These signals are then processed to create an image. The pixel size, color, filters and image resolution are all factors that determine the quality of the image that an image sensor can produce. Image sensors are used in a wide variety of applications. In digital cameras and smartphones, they enable us to capture high quality photos and videos. In medical imaging, they are used for diagnostic purposes such as X-ray and MRIs. Here we can see an 18 megapixel image sensor whose pixel size is 1.25 times 1.25 micrometer. Though we can make small sizes of pixel, it serves us no purpose as reducing the size of pixel further would lead to diffraction of light. That would reduce the quality of the image. Though we could increase the size of the sensor to increase the quality of the image and try not to fit more pixels in smaller spaces. Now we will jump to the CCD sensors. The CCD sensor stands for charge coupled devices. To break down the working of CCDs, we must understand it in steps. First, the light enters the CCD sensors through a lens and falls on a silicon wafer that contains a grid of pixels. Then, each pixel is made up of a capacitor and a photoactive region, where the photon of the light strikes the photoactive region, then releases the electron, creating a charge. Then, the charge in each pixel is shifted to the adjacent pixel through a process called charge transfer. This is done by applying a voltage to the pixel in a specific sequence, causing the charge to move in a precise pattern across the CCD sensor. Then, once the charge has transferred to the last pixel in the row, it is then shifted down to the next row and the process is repeated. This continues until the charge reaches the output node. At the output node, the charge is converted into an analog voltage signal that is amplified and then converted into a digital signal that can be processed by a computer. The CCD sensors have very high image quality, owing to which they are used in the Hubble telescope's Wide Field Camera 3, which has captured stunning images of deep space using CCD sensors. Also in security cameras and surveillance systems, these CCD sensors are used for their high quality. Now we'll jump on to the CMOS sensor. Now we'll jump on to the CMOS sensors. The CMOS sensor stands for complementary metal oxide semiconductor. The light enters the CMOS sensor through a lens and falls on a grid of pixels, same as the CCD sensors. Then each pixel consists of a photodiode, which is a type of semiconductor device that converts the photon of the light into electrical charges. When the photon of the light strikes the photodiode, it creates an electrical charge that is proportional to the intensity of the light. This charge is stored in a capacitor located beneath the photodiode. The size of the charge depends on the number of photons that strikes the photodiode, which is determined by the brightness of the scene being captured. Once the light has been captured by the pixel, the electrical charges are transferred to the amplifier located on the same chip as the pixel. This amplifier amplifies the signal and sends it to the analog to digital converter. Then the ADC converts the analog signal into a digital signal that can be processed by an image processor to create an image. The digital signal contains the information about the brightness and the color of each pixel in the image. The digital signal is then sent to a memory card or a storage device where it can be stored or further processed. In addition to the photodiodes and amplifier, CMOS sensors includes other components such as readout circuit, timing generators, and control logic. These components work together to capture and process the image data in precise and efficient manner. Compared to other type of image sensors such as CCD sensors, CMOS sensors have several advantages, including lower power consumption, higher readout speeds, and the ability to integrate other type of electronics onto the same chip. However, they also have some limitations such as lower image quality, higher noise, and lower dynamic range. Despite these limitations, CMOS sensors are widely used in digital cameras, smartphones, and other electronic devices due to their low cost and high energy performance. There is more to an image sensor. Here we can see the potential wells corresponding to the pixel. But then on the top of each pixel we can see a color filter. A pixel doesn't really know which color of light is arriving there. It is just counting the number of photons. So in order to measure color, we are going to use the color filter sitting just above the pixel. And at any given location, we can only measure one color. After the image is captured, then we can take these individual values of color and interpolate the value to see the actual image. These color filters are also called as color mosaic. Then it is also interesting to see the lens sitting on top of each pixel. The micro lenses take the light from the main lens and focuses the light on active area, the light sensitive area of the pixel. On the left, on the right, we can see a cross section of an image sensor under a scanning electron microscope. And it is interesting to see that the distance between the micro lens and the bottom of the pixel is just 9.6 micrometers. Since we have gathered enough information about CCD and CMOS sensors, now we may compare these two sensors. Overall, both CMOS and CCD sensors have their strengths and weaknesses. While CCD sensors are known for their higher image quality and lower noises, CMOS sensors offer faster readout speeds, lower power consumption, and lower cost. The choice between the two depends on the specific requirements of the application, such as desired image quality, speed, power consumption, and costs. Technology: CMOS sensors use complementary metal oxide semiconductors chip to capture and process images, while CCD sensors use charge coupled devices, capacitors, to transfer charges. In terms of image quality, CCD sensors are generally known for their higher image quality and lower noise than CMOS, especially in lower light conditions. However, recent advancement in CMOS sensor technology have narrowed this gap significantly. In terms of power consumption, CMOS sensors consume less power than CCD sensors because they require fewer components and operate at lower voltages. In terms of readout speed, CMOS sensors are much better than CCD sensors. In terms of price, CMOS sensors are generally less expensive to produce than CCD sensors, which make them more affordable for the consumer electronic applications. In terms of dynamic range, CCD sensors have wider dynamic range than CMOS sensor, which means they can capture more detail in higher contrasts. In terms of size, CMOS sensors are typically smaller than CCD sensors, which make them easier to integrate into smaller electronic devices and further making it more convincing to be used in consumer electronics. Since we looked at the advantages and disadvantages of CCD and CMOS sensors, now we will go into the applications and conclusion of the slides. Both CMOS and CCD sensors have a wide range of applications in various industries and fields. To list out some application of CCD sensors, we have astronomy. CCD sensors are used in telescope and other astronomical instruments for capturing high precision and resolution images of celestial objects. Biotechnology. CCD sensors are used in scientific research and biotechnological applications such as DNA sequencing and microscopy. Same goes for the industrial inspections. High-end photography. CCD sensors are used in high-end photography applications such as medium format cameras for their superior image quality. It is also used in fluorescence microscopy to capture high quality image of fluorescently labeled cells and tissues. Some applications of CMOS includes digital cameras, machine vision, and medical imaging. In medical imaging, CMOS sensors are used in endoscopies and X-ray machines due to their high resolution and low noises. Security surveillances. CMOS sensors are used in security cameras and surveillances for capturing and analyzing video footage. In automotives, CMOS sensors are used in important applications such as real-time image and video processing. In conclusion, both CCD CMOS sensors are essential in modern digital imaging technology. CCD sensors have been standard for many years and are still widely used in high-end applications such as scientific and astronomical imaging. Thank you for listening and have a good day.